Okay, good morning, good afternoon, good evening, and welcome back. So, as you may recall, my brain refused to cooperate at least one point on Friday's lecture. So I owe you something. So basically, I stated something very silly and gave a very good illustration of what happens if you don't take a certain statement seriously and just assume that of course it is trivial. Here is the correct statement. I guess you'll remember what I'm talking about. So if we have a subalgebra of C star subalgebra of C, and UV are unitaries in the big algebra C, then the following are equivalent. Conjugation by U agrees with conjugation by V on the algebra A, if and only if V star U is in the relative commutant, if and only if U star V is in relative commutant. Now, equivalence of 2 and 3 is a triviality. Simply U star V is the adjoint of V star U, and commutant is a self-adjoint subalgebra. There is nothing to say there. Also, equivalence to 1 and 2 is trivial. That is what I proved last time, but let me just say once again. So what 1 says is that UA U star is equal to VA V star for all A in A. Now, if you multiply by, let's say, V star on the left and U on the right, you get exactly what you want. This is V star UA is equal to A times V star U. Right, again, for all A in A, and that's exactly what 2 is saying. Similar statement is that conjugation by U star agrees with conjugation by V star on A, if and only if UV star is in the relative commutant, if and only if VU star is in relative commutant, proved exactly in the same way, or you may just replace U by U star and V by V star. Now, what is the problem is that I was assuming something, but I forgot to say that. My assumption was that both U and V were in the normalizer of A, meaning, okay, so I should define it, I guess. Normalizer of A is set of all W, typically defined for set of partial isometries, but we just need unitaries here. So set of all W such that W star is subset of A, and the second part is redundant for unitaries, but I'll just state it. W star A, W subset of A. Namely, what I was implicitly assuming, but forgot, was that indeed U implements an automorphism of A, not just embedding of A into the big algebra. Because unless you assume that then these three are not equivalent to these three. It's very easy to find examples. So anyway, so this was educational, I guess, just that one should be careful when stating even silly statements. Okay, now that was my past due from last week. Now I have to tell you today's lecture is going to be slightly different than normally. Normally I try to give a non-trivial proof every time because that is what mathematics is about, just having non-trivial proofs. That is not going to be the case today. Basically, I'm caught in the middle between wrapping up one subject and starting another one, and I need to lay grounds for that. So basically, what we'll have is a few sketches of proofs saying that this or that follows easily for what we did so far, leaving those to you as exercises. And also laying grounds for what comes next. So this lecture is going to look more like a colloquium talk than like a lecture. which is again not what a lecture in a course should look like, but just for today it seemed to be the most natural way to go. Okay, so let's go. And let me start with this, wrapping up what we did last time. So last time we defined these subgroups of T to N. Remember, T is unit circle, N is, of course, natural numbers. And remember, we are identifying T to N with the unitary group of L infinity, which we also identify with the subgroup of the unitary group of B of H. So Fe is x in T to N such that delta E of x1 is equal to 0. Remember, delta E is this lim sup of those, maybe I should write it. So delta E is lim sup as n goes to infinity, delta sub En union En plus 1. Here, this is boldface E. So these are those partitions of natural numbers that we have. So Fe is a subgroup, and Ge is the quotient group. And if partition F dominates, if it's greater or equal star than partition E, then this group associated with F is smaller. And because of that, GF is, the group, if F dominates E, then exactly, the group is smaller. And because of that, GE is quotient of GF. And okay, so here is what you have, right? So it's, the ordering goes up. And what we have is this directed system of subgroups sorry, it's not directed system, decreasing family of subgroups of T to N, and inverse system of associated quotients. So lemma that we spent most time last time proving was characterization of when two unitaries are equivalent with respect to VE, and remember what this meant is that conjugation by U as restricted to that algebra Fe was equal modulo compacts with conjugation by V restricted to the same algebra. Right, so we proved that this is equivalent to saying that UV star belongs to this group F sub E. And as I said, this is actually an easy consequence of theorem of Poppas, but theorem is quite deep, so I didn't want to use it. And now from here, we proved the following. This is not how I stated it last time, but this is how the formulation I'll need this time. If you have family E alpha for alpha less than aleph 1, these are families of those partitions of natural numbers into finite intervals. If it is less or equal star cofinal, then this inverse limit of these groups GE has cardinality 2 to aleph 1. Right, so there were only two tricks to the proof. One was that at limit stages of countable cofinality, every element of the inverse limit is realized by a single element of the group, which was just diagonalization of length aleph 0. And the second point was that we can branch, that we can embed the complete binary tree of height aleph 1 into this inverse limit. For that, we needed to know, remember, we had that speed up relation where E was much smaller than F. If for every M, there was element in partition F, which contained M many intervals from the smaller partition. And we used those intervals to produce a unitary which somehow goes around the circle and belongs to the bigger group, but not to the smaller group. So that in the quotient, we can split. We have that kernel is non-trivial. Okay, so this was just about inverse limit of these subgroups inside the circle. And just before I go on, you see cardinality 2 to aleph 1, the cardinality of T to N is 2 to aleph 0. And so if you have continuum hypothesis, this is strictly smaller cardinal, which means that many elements of this inverse limit are non-trivial. They are not realized by element of T to N. So really the right way to look at this is from the point of view of cohomology. I'll give you a reference in a moment. I don't want to go into that, but it's really what is going on, that we have a non-trivial cohomology group here, assuming a continuum hypothesis. And here is a formulation of the theorem by Sam Koski and myself, which is the following. If E alpha for alpha less than kappa, now here kappa is anything, it doesn't matter what it is. It's just that if it's less or equal star cofinal in this space of partitions, then there is an injective group homomorphism from this inverse limit of GE alphas into automorphisms of the Kalkin algebra. And this is exactly what we were proving last time. Right, because to each of these partitions, E alpha, to E alpha, we associated that Banach subspace F of E alpha, and then right, and then to any unitary U alpha, we associate restriction of automorphism to this Fe alpha. And if you have an element of the inverse limit, then lemma that we proved before shows you that thread in the inverse limit defines an automorphism of the Kalkin algebra in a unique way. Now, I stated this for arbitrary kappa because this has nothing to do with aleph 1, but it is virtually impossible to construct this unless kappa is aleph 1, because at stages of uncountable cofinality, this inverse limit typically ends, I mean, not much happens there. Okay, so the reason why I'm saying this is because I want to generalize, to see what happens if you look at other coronas, other than Kalkin algebra. So what exactly was the property of the Kalkin algebra that made this result possible? Let's take a look. So suppose that we have E alpha for alpha less than kappa is less or equal star cofinal in partitions. So for what cyst algebras A, here I'm thinking of, A is going to be sigma unital, non-unital, so that this corona is interesting. So for what A, is there an injective group homomorphism from this inverse limit over alpha G of E alpha into automorphism group of the corona of A? Okay, so one case is called the Kalkin algebra, but what property of the Kalkin algebra was used? Well, here is the first case. So this is again also a theorem of Koski and myself from the same paper. So I'll give you successively weaker conditions that imply a positive answer to that question. And importantly, that means that continuum hypothesis implies that this corona has 2 to aleph 1 automorphisms. Okay, so the first case, if A has an approximate unit, countable approximate unit consisting of projections, with the property that if we take Fn to be a difference between these projections, so that the sum of Fn's converges strictly to the unit in this algebra A, then what you want is that Fm A Fn is non-zero for all m and n. So if you just think about that picture that we had of f of e's before, all the time saying is that no matter how you choose m here, this is fm, no matter how you choose n here, there is going to be something non-trivial in this rectangle here that you'll be able to choose some element of the multiplier algebra. Right? So here I'm thinking of elements of the multiplier algebra as these big matrices over corresponding corners of A. Now, this is exactly what you need to make sure that when you're branching at successor stage, when you choose a unitary which belonged to the previous group F alpha but doesn't belong to F alpha plus 1, that branching actually has different actions on these elements. So just if you have something like this, then you can assure that those automorphisms are different and therefore get a complete binary tree of 2 to F1 distinct automorphisms. Okay, now one interesting, important case of having property 1 is if you just take your favorite unital C algebra, tensor it with compact operators, then you can get approximate unit which look exactly like this, because those compacts exactly behave like compacts behave in the Calkin algebra. You have these non-zero corners, and literally the same proof gives you automorphism as before. But note, A is actually saying more. I'm just assuming that A is stable, not that it is a tensor product of compacts and something unital. So you don't need, basically, in other words, what I'm saying is that these don't have to be projections. You just need approximate unit which satisfies this. Now, before I say why is that so, let me look at the next example. A is primitive. What that means is that it has a faithful non-degenerate representation. Basically, it's far from being abelian. Now, the idea for 2 and 3 is basically you're using this proof here. You don't have projections, but you have quasi-central approximate unit. And that's really all that you need. There are some tricks. I mean, there is no natural separable subalgebra that you have to deal with here, but one can work it out, and Sam and I did work it out. So quasi-central approximate unit, again, our old friend, suffices to prove this. So what we have here is for quite a few separable C algebras, the corona is non-trivial, and basically it's all variations of these conditions here, of this condition here, that all of these corners are non-zero. So you may wonder, what about the opposite situation? So here's the opposite situation. If you have A, which has an approximate unit consisting of projections, but now if you take Fn to be difference En minus 1, then Fm A Fn is 0 whenever m is different from n. Right, so this is completely opposite to the previous one, save for the fact that I have projections again. Well, what does that mean? Well, you see, if I look at F1 here, F2 here, F3 here, and so on, all the elements of A look like that. So this is again F1, F2, F3, right? So they all have zeros here, which means that our algebra really looks like a direct sum of these unit algebras. Okay, well, so A is direct sum of these corners, Fm, A, Fm. Multiplier algebra is the product of those, right? Fm's are projections. And what that means is that the corona is countably saturated, right? So I didn't prove this, but I said that I mean, I gave you reference that this is a theorem, which means that continuum hypothesis implies that this algebra has two telephone automorphisms, and even those automorphisms are much wider. If you just have two elements of the same type, you can find automorphism which sends one to the other. So they're actually much more interesting than the automorphisms which are constructed by using this cohomological trick of embedding these groups. So now you can wonder, well, okay, so does it mean that if I just have a proximate unit consisting of projections, if this doesn't happen, maybe I just have to go to some subsequence. If I cannot get that A is direct sum, maybe I can get that those corners always non-empty. It turns out, surprisingly, that is not the case. So there is a weird ad hoc example of a sigma unit or system algebra in which neither of those two proofs, neither of those two assumptions applies. I'll just leave it to you to work it out. This is, as I said, just a fun little example. And I should say we don't know really, I'll be coming back to this today. We don't know for what coronas of sigma unit or system algebras we can have non-trivial automorphisms. But at this stage, I didn't even tell you what non-trivial automorphism should mean. And I just wanted to spend some time working that out. Any questions? Okay. All right. So let's return before I do that. Let's just return to Calkin algebra. Remember, Brown-Douglas-Fillmore asked a question about K-theory reversing automorphism, observed that such an automorphism would have to be outer, asked, okay, so does Calkin algebra have outer automorphisms at all? And now Phillips and Weaver answered the second question. Yes, under continuum hypothesis, you do have outer automorphisms. But the ones that they or anyone so far constructed are not going to be K-theory reversing because they're locally inner, that they are implemented by unitaries on separable subalgebra. So this question is wide open. And even easier, presumably question is open, is it possible to find in some model of ZFC an automorphism such that its restriction to some separable subalgebra is not implemented by unitar? We don't know. Now, I mentioned this Rudin's sigma to 1 absoluteness theorem. Essentially, what that theorem implies is that if you're trying to find, to give positive answer to any of these two questions, you might as well assume continuum hypothesis. It's not really saying that a positive answer, if there is a positive answer, if there is some model of ZFC, then positive answer holds in a model of continuum hypothesis. It doesn't literally say so, but basically it says so that if that's not the case, then you would have to use some quite non-conventional methods to prove that. And assuming that set theory is sophisticated enough at this point, basically it is pretty much safe to assume that if just assume continuum hypothesis and try to prove this, which in turn means that there is no set theory left here, really. I mean, question at this point is non-set theoretic, and it is not even clear whether there is any model theory left in it, because any model theoretic approach to this question failed. So that the Calkin algebra is not countably saturated, not countably homogeneous. We don't know what are types of shift or its adjoint. And even if we did, we wouldn't know what to do with it, unless they're different. But yeah, we don't know that. So it seems that once again, we are at the brick wall and some completely new approach is needed here. And that's all I have to say about these questions. So okay, actually, we'll come back to it for the other side of the coin of the Phillips-Weber theorem. But for now, let's just move on to other coronas. Any questions? Okay, so when does the corona of A have many automorphisms, assuming continuum hypothesis? Let me look at the abelian case. So this is a case that has been studied independently from C-star algebras by topologists for quite a while. It is much better understood what is going on here. So what do we have? We have A. It is, if it is non-unital abelian separable C-star algebra, then it is isomorphic to C0 of X. X is locally compact and metrizable. And the multiple algebra of A is isomorphic to continuous functions on beta X, the checksum compactification. And the corona is isomorphic to continuous functions on beta X minus X. Okay, so let's look at what can we say here. So first, easy case, if you can write X as an increasing union of clopin compact subsets, K of n, you know, something like, let's say, direct sum of countably many copies of unit interval, or countably many copies of Cantor space, or basically anything you can partition into compact clopin sets, then A is direct sum of continuous functions on these. You see, because Kn minus 1 is both closed and open, this is a closed set. So A is direct sum of countably many unital C-star algebra. So, yeah. And therefore, the corona, M of A mod A, is countably saturated. Again, so continuum hypothesis implies that it has many automorphisms. Okay, now, for something like this to work, you don't really need a partition of all of X into clopin compact subsets. Even if you have a non-compact open subset of X, sorry, a non-compact closed subset of X, which can be partitioned like this, then if you can find automorphism of that corner, it extends to automorphism of the whole thing. So basically, the interesting case really is what if X is connected? In a sense, opposite case of this here. And the first most obvious case was solved by you back in the 80s, I think. If A is C0 of R, then continuum hypothesis implies that the corona has 2 to alpha 1 automorphisms. Again, you was working from topological point of view. He was really looking at the checksum remainder, well, not really of R, but of the half line, 0 infinity. But basically, corona of R is just a direct sum of 2 copies of that. The space beta this minus this is a continuum. It is a connected compact Hausdorff space. So this was really a study of large, massive continua. Use proof is just by hands, by looking at the different topological properties. And it just doesn't work for R squared. Alessandro Vignati in 2017 extended use result to arbitrary C0 of R to the n for any n. And basically, he did this for all sorts of manifolds in a very, very general situation. So it's a very nice and short paper and very clever trick which constructs a lot of automorphisms for these coronas. Now, the explanation of use result is that the corona of C0 of R is countably saturated. This result came many years after his result. And the proof is different from the other proofs of countable saturation. And now you may wonder, is there similar explanation for Vignati's result? So what about coronas of C0 of R to the nth? Well, they're probably not countably saturated. So there is some evidence that these automorphisms don't come from countable saturation, but no concrete result yet. Okay, so again, still considering the abelian case. Now, if X is zero-dimensional, namely if it has a basics consisting of sets which are both closed and open, then okay, we have Gelfand-Naimark duality between C-star algebras and topological spaces, but we also have stone duality between compact zero-dimensional spaces, stone spaces, and Boolean algebras. So here is really the picture. We have on the left C-star algebras, C0 of X, its multiplier algebra, and the corona. They correspond to topological spaces X, beta X minus X. Now, in case of X, there is no Boolean algebra really here. There is an ideal in Boolean algebra. X is not compact. But if beta X is compact, you can just look at the algebra of closed and open subsets of X. And then you can recover beta X. Oh, it should have been Klopen subsets of beta X. And sorry, let me just draw this properly. So this is Klopen of beta X. And this is, oh no, it doesn't matter. Sorry, what am I saying? Yeah, that's fine, that's fine. So Klopen subsets of X, if you look at Klopen subsets of X, they're really the same as Klopen. It's isomorphic algebra to algebra of Klopen subsets of beta X. And beta X is the stone space of that. If you remove X, what you're really removing is compact Klopen subsets of X. This is an ideal of the Boolean algebra, and the quotient is this. So we have equivalence of these three categories, and one can, when trying to understand automorphisms, look at either one of those categories. Right? If you have automorphism of this Boolean algebra, it corresponds to autohomeomorphism of the compact Hausdorff space, and automorphisms of compact Hausdorff spaces correspond to automorphisms of these C-star algebras. This equivalence here, the Gelfand-Naimark part, does not depend on Boolean algebras, but just it is just easier, and traditionally it was done way earlier to understand what happens with Boolean algebras. Right, and now let's look at the easiest of all cases. Okay, so what is the simplest locally compact, non-compact Hausdorff space? Well, just the infinite discrete space. So just look at C0 of the natural numbers. And here is what the previous table becomes here. C-star algebra, so C0 of X is just little C0. Multiplier algebra is L infinity. Sorry, my computer complains that I have low battery. Just make sure nothing bad happens. Okay, let's see. Yeah, we are good now. So multiplier algebra is L infinity, and the corona is L infinity mod C0. In terms of topology, you have natural numbers, beta n and beta n minus n. So basically, we are talking about space of non-principal ultrafilters for natural numbers. In terms of Boolean algebras, this is just power set of natural numbers, right? All subsets of discrete space are open, and the compact subsets are finite subsets. So we're talking about the quotient P of n modulo finite. And this is an object that set theorists, combinatorial set theorists, devoted a lot of energy to, and it is well understood, and it is quite horrible from set theoretic point of view. Basically, most non-trivial statements about it are independent from ZFC. Right. Okay. So let's take a look. Now, the earliest result in the subject goes back to Walter Rudin from the 50s. His motivation was different from our motivation here, but I just want to say one word about it. It was about homogeneity of topological spaces. So topological space X is said to be homogeneous if its auto-homeomorphism group acts transitively on X. Namely, if you give me any 2 points, X and Y and X, there is auto-homeomorphism which moves one to the other. And back then it wasn't obvious. You see, if you look at algebra, algebra P of n mod finite, this algebra is homogeneous. It looks everywhere the same. I mean, this is an exercise. It's a theory of atomless Boolean algebras has elimination of quantifiers. All non-zero elements look the same except for the identity, of course. So it was perhaps natural to think that maybe the space, its tone space, is also homogeneous. But Rudin proved, assuming continuum hypothesis, that beta n minus n is not homogeneous. So in other words, what he proved is that there are at least 2 kinds of ultrafilters with the property that no auto-homeomorphism sends one to the other. And, nowadays it is easy to see what those are. They actually have a name, p-points. I think that the name may go back to Rudin. What can you construct using continuum hypothesis? Well, just enumerate all subsets of natural numbers by Aleph1, by countable ordinals. Now you can choose a decreasing sequence of subsets of natural numbers, which is decreasing modulo relation subset star. So X is subset star Y if and only if X minus Y is finite. Now, with this relation, if you have a decreasing countable sequence, then by a diagonalization argument, you can find an infinite set which extends it. And therefore, by diagonalization, you can construct an ultrafilter which is generated by a decreasing Aleph1 chain of subsets of natural numbers. That ultrafilter has the property that if you take any countable family of its open neighborhoods, its intersection again contains an open neighborhood. Because this countable family, those open neighborhoods, their openness is verified by first countably many elements of your sequence. And then there is further set which is contained in all of them modulo finite. And okay, so those are p-points. Now, and you see any auto-homeomorphism sends a point with that property to a point with that property. Now, the fact is that not all points can be p-points, because if you just take a countable subset of beta n minus n, its closure has to have, I mean, that countable subset has to have accumulation points. And if point is an accumulation point of a countable set, it is not going to be a p-point. Because for each one of those points, you can pick an open neighborhood which doesn't contain it, so that their intersection cannot contain open neighborhood because your accumulation point. So this was Rudin's motivation. This was somewhat something of a digression, but I mean, one of the consequences of what he did was that he proved, okay, his formulation was that beta n minus n has 2 to aleph 1 auto-homeomorphisms, although really what he was doing is constructing automorphisms of P of n mod phi. But what we really care about here is that L infinity mod C0 has 2 to aleph 1 automorphisms. What Rudin proved is that all of these p points look the same under continuum hypothesis. If you give me any 2 p points, there is auto-homeomorphism which sends one to the other. So the action is transitive on p points. Now, we can give 2 proofs of Rudin's theorem now from what we did so far. One way to think about it is L infinity mod C0 is countably saturated C algebra. Right? It is reduced product, they are countably saturated, and therefore under CH it has lots of automorphisms. Another proof which has been used, I mean, versions of this have been used by general topologists, is to look at this Boolean algebra, P of n mod finite. It is a countably saturated Boolean algebra, and therefore it has 2 to aleph 1 automorphisms. Now, I should say that these two are really different statements. You do have equivalence of categories, but countable saturation really depends on the language that you choose to axiomatize your theory. So countable saturations of these two objects are really independent theorems. It's not that one of them implies the other, just that they have the same consequences for our purposes. All right. So as I said, this today is more like colloquial talk, but those are just things that I feel I have to say in order to make sense. And I can promise next time we'll have more proofs, definitely. Okay. So another important digression, I would say, this is important digression. Kuhn proved in the 70s that beta n minus n is not homogeneous in ZFC. He used extremely clever construction of ultra filters, and that construction was really understood and brought to a new level by Sachar and Scheller, and he used it to construct ultra filters while controlling what ultra powers look like. And this is exactly behind theorems that I mentioned before, that under continuum hypothesis, there are many 2 to aleph 1 non-isomorphic ultra powers of any separable infinite-dimensional C algebra. So Kuhn's construction, as modified perfectly by Schalach, enables you to construct an ultra filter and at the same time control what an ultra power looks like. And this is ZFC construction. So it's just continuum hypothesis is only used to well, yeah, sure. This is ZFC, so you don't need continuum hypothesis for this. Okay. So let's go back to our story. So question is, what can we say about Rudin's result? Is continuum hypothesis necessary to construct many non-trivial automorphisms of L infinity mod C0? And also, this word non-trivial, what exactly do I mean by that? So really, what makes an automorphism non-trivial? And this is what we should understand before we go on. Now here, and okay, what I want to say again, this is again digression, not about C algebras, but basically two extreme cases that tell us that answer to this question may really depend on the category in which we are working. So let's take a look at those cases. Look at this group. Look at Z mod 2Z, just the two element, no, cyclic group of order 2, product of countably many copies of it, modulo direct sum of countably many copies of it. Now, as a group, this is really, to a set theorist, this is just a power set of n modulo finite with respect to symmetric difference. Right. So each generator just corresponds to a singleton in natural numbers. That group has 2 to the continuum many automorphisms in ZFC. So the analog of Rudin's result here is true in ZFC. If you just forget about some of the Boolean algebra structure, just keep the symmetric difference, you get this. Now, I called it exercise, but I should probably tell you what is going on. Just look at F2, the 2-element field. This here is a vector space over F2. Right? You can multiply by elements of F2, and there is a natural addition of vectors. And its dimension is 2 to all of 0. Basically by counting argument. So its cardinality is 2 to all of 0. And for finite field, for infinite vector spaces, dimension is the same as cardinality. And then it's just linear algebra. Right? You have 2 vector spaces. I mean, you have a vector space, then any permutation of the basis corresponds to automorphism at vector space. And vector space actually has more structure than this group. So every automorphism of the vector space is automorphism of the group. And therefore, we have 2 to the continuum many of them. And even more, if you just look at P of n with symmetric difference, that's even isomorphic to this. So taking quotient doesn't make any difference. And I mean, this is one of my favorite things that I would like to understand better. What exactly is going on here? Why this theory here has this property that in ZFC you can construct many automorphisms, and in some other theories, as we'll see soon, that is not the case. I mean, there are model theoretic explanations of this, but what I would really like to see is some sort of dichotomy theorem, just saying that if you have a category like this or theory like this, then you have lots of automorphisms in ZFC because theories are stable, omega stable, or something like that. But otherwise, if your theory has order property or something like that, then the question is independent. And in some models of ZFC, all automorphisms are trivial in certain sense. Right, so the reason why I'm dwelling on this example so much is that basically here, no matter how you define non-trivial automorphism, this has non-trivial automorphisms. They're all fine. Now, the opposite situation is something that we'll come back to in a moment. Almost permutation of natural numbers is a bijection between cofinite subsets of natural numbers. So interesting example is f of n is n plus 1 for n in n. Right, so this is almost permutation. And now, if you look at almost permutation of natural numbers with respect to composition, a composition of 2 almost permutations is almost permutation, right? Because both domain and codomain are going to be cofinite. And now look at permutations which are finitely supported. What I mean by this, I mean f in S infinity, right, the permutations, such that f of n is equal to n for all but finitely many of the n's. Right, so the place where something non-trivial is happening is finite. Now, these are all almost permutations, and this is, I'm not sure if you want says normal sub-semigroup, but one can take the quotient. You can take the quotient structure, and that quotient structure is a group. Right? So you're starting from a semi-group, right? There are non-invertible elements like this one, but when you mod out by permutations with finite support, even things like this have inverse. Basically, the F inverse just sends n plus 1 to n for all but finitely many n's, and for those for which is not defined, doesn't matter, because after modding out by this, you get proper inverse. So this is a group. Okay, their theorem wasn't that this is a group. This is that was clear from the beginning. Actually, they're not stating it even this way. But what is important here is that every automorphism of that group is inner. So it is implemented by an element of the group in ZFC. Right? So you see, these are completely opposite situations. Right? So here, this structure is as rigid as you can imagine, and this one is as non-rigid as you can imagine. The way that they stated result is really that if you look at S infinity, group with all permutations, modulo these finitely supported. I'll just say fin S infinity for finitely supported permutations, the outer automorphism group of this is isomorphic to Z, and those automorphisms exactly come from, they're generated by conjugation by this element here. So essentially what you have is Fredholm index coming in here. So you're really conjugating by shift, and up to inner automorphisms, those are the only automorphisms that exist for this structure. I'll be coming back. This is a beautiful combinatorial construction. With the way that you can code automorphisms in this structure. Right, okay. But let's go back to our questions. So what we want to understand in general situation, the following: we have M and N, their structures in some category. Just think cyst algebras, and you have isomorphism between quotient of M and quotient of N. Here you have quotient maps. Now what you want is to understand how can this isomorphism be lifted? Namely, how can you complete the diagram? Depends what restrictions you impose on this question mark here. If you don't impose anything except the diagram commutes, you can just use axiom of choice, and for each equivalence class, just choose representative and find some function that sends M to N, so a diagram commutes. In general, you may want to lift isomorphism by something that actually agrees with your category, but by maybe isomorphism between M and N, or at least homomorphism. You see, lifting by an isomorphism is generally too much, which is clear from this example of Alperin, Covington, McPherson, right? You cannot, if you have isomorphism which corresponds to a shift, you cannot lift it to an isomorphism, but you can lift it to something that is close enough to isomorphism. So let's see what happens with cyst algebras. And this is what I call algebraically trivial automorphisms. Let's just look at the category before we mod out. This every automorphism of the algebra P of N is of the form X goes to F inverse of X for some permutation S infinity. Now proof, this is really triviality. So what do we have? Well, we have phi of some singleton M is going to be singleton, because phi's isomorphism, this singleton M is an atom, it has to be a singleton. So if phi of M is equal to some N, then just let f of N be M, this defines function M uniquely, right? So this is a bijection, and you just check it works. Right, so it's just this ability to go down to atoms and to define it piece by piece that makes this possible. Related exercise, every automorphism of B of H is inner. The main idea is similar, but you just have to work slightly harder, because now you have projections of rank 1. Automorphism sends projections of rank 1 to projections of rank 1, but you just have to figure out how to construct a unitary. So I'll just leave it to you. You just have to make some choices. So I'll leave it to you. Okay. So, and here is what I already said in a slightly different way. P of n mod phi has an automorphism that cannot be lifted to an automorphism of P of n. And automorphism, I think it's on the slide, right? So just take the following function. So x goes to set of all n minus 1 for n in x. Just look at conjugation by shift. This is lifted by a homomorphism of P of n, but not by an automorphism, because the kernel is going to be trivial no matter what. Let me know if there are questions.
Can you repeat that, please, Ilijas, about why this cannot?
So our phi of the equivalence class of x is the equivalent. So this is equivalence class modulo finite. Is the equivalence class of n minus 1 for n in x mod finite. Now, why is this not lifted by an automorphism? Well, every automorphism corresponds to a permutation, is lifted by permutation. Now, what would that permutation be? So, okay, so if phi was lifted by a function of the form x goes to f inverse of x for some f in S infinity, then what would we necessarily have? You can see there is something funny about today's lecture, because this is the first time I'm doing this today, right? So this is quite unusual. Then what would we have? Well, we would have that f of n would have to be equal to n plus 1 for all but finitely many n. Right? If you have infinitely many n, such that f of n is not equal to n plus 1, right? So if set of all n such that f of n is not n plus 1 is infinite. Okay, so now I have my notation is not great here. So if x is this, then okay, we can go to thinner subset. So that then fine, let's call it y subset of x infinite, so that for all n, if n is in y, then n plus 1 is not in y. I just want to space it out a little bit to avoid something funny. So then, if I take z to be n plus 1 for n in y, we have that phi of the equivalence class of z is the equivalence class, well, it is the equivalence class of y, right? Because this is how we define the function. But if you look at f inverse of z, this is even disjoint from y. Because f of n is not n plus 1. Oh, okay, I should have been more careful. Let's see. So this is true, and also f of n plus 1. I think I want this to be basically just spaces it out enough to avoid having something like this, and you get this. Right. Okay, so so the right definition here is that automorphism of P of n mod finite is trivial if there is a bijection between cofinite subsets of natural numbers with the property that x goes to f inverse of x lifts phi. And these are exactly those almost permutations from Alperin, Covington, McPherson theorem. And here is a remarkable result of Shellac from, I'm not sure, I think it's 1979 or something like that. If ZFC is consistent, then there is a model of ZFC in which all automorphisms of P of n mod finite are trivial. In particular, there are only 2 to F0. There are only continuum many automorphisms of P of n mod finite in that model. So it's really this result that basically started the entire subject and gave hope of proving similar results for other objects, such as the Calkin algebra. Now, note, this was actually proved shortly after a Brown-Douglas-Fillmore question, but probably nobody was aware of both the question and the Shellac's results. So, to me, this is one of the, I mean, if you take from this course one thing, just, it's good to know different things and to look out and see whether what you know can be applied elsewhere. So it's really, I mean, mathematics is a bit too specialized nowadays, and it is, there are quite a few subjects that can be applied to other subjects in somewhat surprising ways. This is just one example of those. All right, enough talking. So let's go back to this. So what do I want to do right now? Well, you see here we have this definition of trivial automorphism, and Shellac's theorem tells us that indeed this is the right definition. Why? Well, obviously anything that satisfies this here is an automorphism, right? If you can find a function phi f like this, then phi is going to be an automorphism. And to me, the right way to interpret Shellac's theorem is to say, well, there is no other way to construct an automorphism of P of n mod finite. If in ZFC you can construct an automorphism, really, you have to find a function f like this. Anything else is not going to exist. And actually, if you look at his proof, it is quite involved oracle chain condition construction. Oracle chain condition was specially invented for this purpose. You basically look at automorphism, see if it is not trivial, and somehow extend the model of ZFC to something in which that cannot be extended by an automorphism anymore. And there is a very tricky bookkeeping to make sure that you never resurrect those automorphisms that were destroyed. So this is a beautiful proof. One somewhat unsatisfactory aspect of this proof is that on one hand, continuum hypothesis is something that every functional analyst can easily understand, probably every mathematician can understand and can use. Shellach's model is just an ad hoc construction of a model of ZFC. So basically it leaves a question, well, I mean, if there is just some unnatural model of ZFC in which this happens, should we take this statement seriously or not? That's always a question. But in this case, there is a better answer to that question. So, oh yes, and another thing, something that I said before, that because continuum hypothesis is a very strong axiom, its negation is a very weak axiom. So it doesn't really imply many things. And in particular, not here, if ZFC is consistent, then there is a model of ZFC in which continuum hypothesis fails, and yet P of n mod phi has non-trivial automorphisms. And even a model is a bit more natural than one in Shellach's theorem. It's actually original Cohen's model for the negation of continuum hypothesis. Right. So after this, you may wonder, are those models in which all automorphisms of P mod phi are trivial are just some peculiar rare objects? So let's take a look at this. Yeah, okay, I'll leave this slide for later on. I'll just keep it. Let's take a look at what exactly does it take for an automorphism to be trivial. So basically, question is what exactly does it mean to be a trivial automorphism? So here's one lemma that gives us some idea of how to proceed. Let me just say why am I doing this? You see, we saw a moment ago that you cannot hope to lift an automorphism to an algebraically trivial morphism. So instead of proceeding by looking for algebraically trivial morphisms, we'll look at topologically trivial morphisms. And for that, we need a nice topology on our algebras. So if A is separable, then strict topology on the unit ball of M of A is Polish, namely separable and completely metrizable. What is the reason for that? Well, this topology is given by countably many semi-norms. Remember, strict topology was defined by looking at those semi-norms. A goes to little h, norm of HA, and A goes to norm of little AH. Now, you have these countably many semi-norms. They're all bounded by 1. They're all dominated by the norm. And therefore, you can just sum them up, 2 to minus n times the nth norm. This gives you a metric. And that metric is complete. And it is also, the space is separable because A itself is dense in it. So this space, the unit ball, with respect to this metric is what is called the Polish space. And those are nice spaces that descriptive set theory can handle. I should say that there is a horrible mistake in my book. It's not, M of A itself is not Polish. It is unit ball that is Polish. And if you look at the lemma where I'm claiming that M of A is Polish, it's actually proving that unit ball is Polish, but it's, yeah, okay, wrong. Now, once you have nice topology, then space sets which are nice with respect to it are going to be well behaved. So if A is separable and unital, we say that automorphism of the corona is topologically trivial if the following set here, this is really a graph of the function of phi on the unit ball. So you're just lifting all possible pairs A and B. So we ask this to be Borel in the strict topology. why is this the right definition? Well, it works. So what is the point here? By a theorem called Schoenfield's absoluteness theorem, if you have a Borel subset of m of a, this should be squared, of m of a squared, which is obtained like this from an automorphism of m of a mod a, that property is absolute between transitive models of ZFC. So basically, it shares one property with algebraically trivial morphisms in that if you can define it, then it doesn't depend on the model of ZFC in which you are. So this Borel set, it's this property of lifting and defining an automorphism is invariant under model of ZFC that you take. And therefore, just asking to have triviality in this sense is reasonable until we come up with a better definition. That's still, I mean, basically this is a work in progress. Now, in short, what is the outline of proofs that all automorphisms of Kalkin algebra are inner or similar results? Well, you assume that you're in some nice model of ZFC. I'll say more about that. Prove that your automorphism has topologically trivial lifting, and then forget what model of ZFC you're in. Then you're just working in ZFC, and prove that in your specific situation, if you have topologically trivial automorphism, then you actually have trivial automorphism. And trivial may mean inner, but it's not going to be inner if your algebra is abelian, for example. Abelian algebras have no non-trivial, no interest in inner automorphisms. So really, this definition gives you sort of halfway what trivial should mean. Right, and here is a conjecture by Koski and myself. If a separable non-unital Swiss algebra, then continuum hypothesis implies that M of A mod A has topologically non-trivial automorphisms. This is weaker than has 2 to aleph 1 automorphisms. Why? Well, because continuum hypothesis implies that 2 to aleph 1 is greater than aleph 1, and there are only aleph 1 Borel subsets of any Polish space, any fixed Polish space. So if you construct 2 to aleph 1 of them, then there are going to be many of them are going to be topologically non-trivial. So basically what I was saying before, all of those special cases, those were instances in which this conjecture has been confirmed. And it is still open in general. So that there are still few cases in which we don't know whether it is true. Right, so as I said, that there are several partial positive answers here. But what I want to say now is really going from automorphism to topologically trivial. Right. What sort of model of the ZFC does it take to prove that every automorphism of certain structure is topologically trivial? Now, you see, this is going to work for Cis algebras, but it doesn't work in every category. Remember that example of a quotient group. And right, so here it is. So this conclusion of Sherlock's theorem that all automorphisms of pure mod fin are trivial is actually true in a large class of models of the ZFC which are canonical in some sense, or at least they satisfy certain canonical axioms. So these are so-called forcing axioms. I just wanted to say in general what they are, although axiom that we'll be using is a bit easier to state. So suppose that omega is a class of compact Hausdorff spaces. Then Fa omega is the following statement. If you have a compact space in class omega, then intersection of any family of Aleph1 dense open subsets of K is dense in K. So here is one example. If you have a unit interval in omega, then Fa omega contradicts continuum hypothesis. Why is that so? Well, for every singleton, look at set, just remove that singleton from 0, 1. Look at 0, 1 minus x. If there are only Aleph1 many real numbers, there are only Aleph1 many sets of this form. Each one of them is open and dense, and their intersection is going to be empty if you enumerated all real numbers. So, so this, even forcing axiom for this space is asserting that continuum hypothesis fails in a specific way. Now, if you just look at other compact metrizable spaces, it's always the same axiom. There is no, well, okay, without isolated points. If it's non-trivial, then it's the same axiom. But as you get a bigger and bigger class of compact Hausdorff spaces, you get more and more interesting axioms. Some of them are too interesting. Some of them imply that 0 is equal to 1. It is not difficult to find compact Hausdorff space and family of Aleph1 dense open subsets whose intersection is empty in ZFC. So really in this Fa omega, everything depends on this parameter omega. And a lot has been done on understanding what can be put there. And now we understand it quite well, but definitions of those spaces are usually quite mathematical. So some axioms that you may have seen, Martin's axiom, proper forcing axiom, Martin's maximum, we'll be using a consequence of proper forcing axiom, which is independent from Martin's axiom. I'll not be using forcing axiom directly, but I just really think it is important to have the context here because these rigidity statements about all automorphisms of this or that being trivial are really true under certain nice canonical assumptions, and those are forcing axioms. Right. Okay, so here is this. Remember, Sherlock proved, just constructed some ad hoc model of ZFC, but later Sherlock and Steptrans proved that proper forcing axiom implies all automorphisms are trivial. And then in a really beautiful proof, Velichkovich proved that two consequences of proper forcing axiom, Martin's axiom and OCA, which we'll see next time, they together imply that all automorphisms are trivial. And he also proved that Martin's axiom alone does not suffice. So, which gives us yet another model of ZFC in which P of n mod fin has non-trivial automorphisms. I mean, this here, I'm just putting it, if there are some peak logicians, basically, we don't know that ZFC is inconsistent. So if it is inconsistent, then MA implies everything, including that all automorphisms are trivial. Right, so I still have just a little bit of time here. So I just wanted to put all the talk in this lecture. So what I want to say next is another motivation, in addition to Brown, Douglas, Fillmore, for why we might want to understand automorphisms of coronas. And now you can move on and actually ask, well, why just automorphism? Why not isomorphism? because you know, if you can lift automorphisms, maybe you can lift isomorphisms, and then you can try to understand how relations between coronas lift to relations between the original algebras. And there is a question of Sakai from 50 years ago that serves as a motivation for this. So here is the question. If A and B are separable and simple cyst algebras, does the isomorphism of their coronas imply that algebras are isomorphic? You may wonder why assumptions, separable and simple, well, each one of them is maybe not technically necessary, but if you drop either one of these assumptions, there is a counterexample. For simple, there is a very easy counterexample. If you just take something like A direct sum with C, if you make sure that C is unital, then corona of this, basically C disappears. Corona is isomorphic to corona of A. So if you don't insist on simplicity, you can just cook up very silly examples. Separability is more interesting case. You see, I proved a few classes ago that if you have alpha power of separable infinite dimensional cyst algebra, then its corona, its alpha power is non-separable. It has density character continuum. Very similar proof shows that if you have corona of separable non-unital cyst algebra, sigma unital, then its corona has density character continuum. But you need separability for that. So there is an example of Sakai. There is a simple non-separable non-unital algebra A whose corona is isomorphic to complex numbers. And corona is really obtained from 2-1 factor by taking a maximal proper left ideal of it. And the corona is just 2-1 factor again. So the quotient is just the complex numbers. Very nice proof. So in this case, you see, you know, that there are going to be many non-isomorphic algebras like this. So this is necessary. And just one more thing I wanted to say. From set theoretic point of view, we don't really have any non-trivial answers to Sakai's question, although I'm quite sure that there should be many, that we should be able to construct something here. But there is a very nice result of George Eliot from 1973. He gave positive answer to Sakai's question for the matroid algebras. So these are algebras which are inductive limits of full matrix algebras, but not unital, right? If it's unital, then it's UHF, corona is trivial. If you have non-unital one, so by using essentially K-theoretic methods, Eliot was able to find an invariant which distinguishes between coronas. Yeah, which puts this sort of abstraction to constructing isomorphism like this. Okay, so right. So for the next time, we'll actually have you know, mathematical lecture with proofs again. So let me just recap what I was doing right now. So we wrapped up the continuum hypothesis part. We started the forcing axiom part, and we'll see there is another conjecture that under forcing axioms, all of these coronas have the isomorphisms between coronas of separable cyst algebras do have topologically trivial liftings, and we know much more about that. So we'll start working on that next time. Okay, any questions?
Ilijas, can you repeat which is the difference between AM and UHF again, please?
So UHF is unital. So, basically in AM, in the AM case, you have, I mean, basically, if you just take, for example, compact operators are AM and definitely not UHF. Or if you tensor compacts by the car algebra, it is also AM but not UHF.
I see.
But this is not all. You can have AM algebra which has finite trace. Any other questions? Okay, so if not, thank you, and I'll see you on Friday.